It's my pleasure to introduce Art Owen, who's giving our first seminar from an outside speaker of the semester. And he'll be talking about backfitting and cross-random effects. And I just wanted to remind everybody that feel free to leave your camera on if you'd like, no pressure, but it does, I think, help a little bit with the interactions. And I also wanted to remind everyone that we will have a sort of post-seminar discussion, but it'll be tomorrow at noon Eastern time. And I just want to invite everyone who's interested to come join us then. Without further ado, though, Art, you can take it away.
Well, thanks, Walter. Are my slides visible enough? If I go full screen, then I can't see any of you. So
they're like half screen, but that's probably.
I'll go full screen, then maybe I'll jump back later. Okay. So I'm here to talk about backfitting and cross-random effects. This is joint work with my colleague Trevor Hastie and our student Swarnadip Ghosh, and there is an archive link, so we posted it to archive. Well, okay, summary. Cross-random effects are pretty common. You could have plant varieties by environments, customers and products. Anywhere there's a many-to-many mapping, you could be looking at cross effects, and often you want them to be random. And there's this nasty thing that even a simple model, it's going to cost you n to the 3 halves work to compute it. And my former student, Caitlin Gao, did lots of work on this. It's their inner thesis and some of our joint papers. So n to the 3 halves, that's bad luck if you want to go with big data. You can't really have anything. You can't tolerate n to the 3 halves. I mean, you might even hate n log n. And what we're going to do is we're going to get it down to order n. And we're going to use backfitting. And this is an old idea, comes from a paper by Buya, Hastie, and Tibshirani. So we'll do backfitting, and then it'll be order n. And we're going to do linear models. So we're going to do generalized least squares. And we have cooking generalized linear mixed models. Okay, so we have something, I'll say real soon now, which means it feels like it's soon, but you never know. And we have a data example. We have 5 million ratings from Stitch Fix. So huge thanks to Brad Klingenberg. So Stitch Fix will send samples of clothing out to people, and then the people maybe they buy them, maybe they send them back, maybe they like them on a 10-point scale, maybe they fit or maybe they don't. So it's an interesting data set. Okay, I'll start with categorical variables. When we teach about a categorical variable, it might be something like it was a treated or an untreated person, or it was 3 kinds of iris flower, or the 50 US states. Those are categorical variables that fit into a lot of our models. And what do we usually do? We turn them into dummy variables, indicator variables, one hot encoding, 3 names for the same thing. That's what we do with them. We just turn them into binaries and just treat them as regressors. Well, there are some problems where that's not quite what you want to do, or I think that's not quite right. Some of these settings are really different. So suppose you have a product ID, stock keeping unit. Like suppose the customer wants a dust filter for a Hoover Max Extract Pressure Pro Model 60. If that's what they want, then there's really nothing else that's going to work for them. And so that means there's a lot of levels for that product. There could be thousands or millions of different levels. That's different than 3 kinds of iris when there's millions of levels. Also, at a web company, the query string you type in when you're doing a search, well, that's a categorical variable with a lot of levels. So maybe somebody typed in COVID or Biden. Maybe somebody typed in heteroskedasticity. That's one of my favorites. And SUTFA is another one. Well, what you notice is that some of these queries are going to be a lot more popular than others. At a place like Google, every day they'll get some query that has never been seen before. Another variable like this, a customer ID, or a URL or an IP address. And those things churn. They show up, especially if it's a cookie. Cookie comes, cookie dies. So they're not constant. Now, okay, so there could be millions of levels. There could be a power law frequency between popular and unpopular. And there could be a constantly changing set of levels. Now, we might want to treat these factors as random effects. And I'm not going to say you have to do that. Maybe you have another way to think about them. I actually don't think random effects is the perfect way to think about them. But what bothers me is that if you wanted them to be random effects, you couldn't have it. The computation grows as n to the 3 halves. Why can't we have nice things? I would want to be able to treat those as a random effect. Okay, cross-random effects. I mentioned customers and products in education, students by questions, agriculture, it might be genotype by environment. Yelp might care about this diner at that restaurant. Amazon might say, well, you read that review, you bought this book, you sent it to that address, you paid with that credit card. So there could be 4 of those factors, all with a great number of levels. Anytime there's a many-to-many relationship among things like this, well, you can get a crossed structure that I think you want to treat as random effects. Okay, here is the simple model that we're going to look at. And we look at it because it's the simplest model that we couldn't do until now. So we have a response Yij. So customer I, product J. And we could fit a regression model. Okay, we have features. The feature can depend on the customer, the product, or both, and a regression coefficient beta. Then we put in a random effect for who the customer is, a random effect for what the object is, and a noise term. And let's just suppose those are all independent, mean zero, variance sigma A squared, B squared, and E squared. This is a really modest model. If you think in neural net terms, it's only got 1 layer, and the layer is linear. So it's not like a deep anything. It's a very plain, simple model. Once you fit this model, you can't learn like movie genres, you can't discover communities of users, any of that. If you know a community, you can bake it in with your known X's. But if you wanted to discover, say, a topic or use it for recommendation, the most you could do is you could say, well, this B is really big, so everybody likes product J. Or if it's small, everybody doesn't like product J. That's not the same as customization or anything. So this is a very plain model. And yet, it's hard. Why is it hard? It costs you n to the 3 halves to calculate the likelihood just 1 time. That's kind of a surprise. I mean, that model looks like it could have been in the late 40s, early 50s. And here we are, we're well into the 21st century. And yet this very plain model, it's hard to do. Okay, so it's going to cost you n to the 3 halves to fit this. At least it would have. And when people hear that, they say, well, you should just use a Bayesian method. So let's just be Bayesian. Well, it turns out if you're Bayesian here, if you run a Gibbs sampler, it'll take you about root n iterations to converge. And each of those iterations will cost you about order n. And you're right back at n to the 3 halves. And I think there's a hidden law of nature here that says the Bayesian cost and the frequentist cost, they're kind of stuck together. Okay, well, why do we even use a model? We want to use it so that we can generalize from numbers we have to numbers that we don't have. And we need to use replication to make that go. You know, things are repeatedly happening. We believe that they'll keep happening in the future. And so nothing is easier than IID setting for that. So if you have a model where everything's IID, then, you know, then it's pretty easy to think about generalizing from the data you have to the data you don't yet have. And hierarchical data, they're kind of easy too. You might have some dependence inside clusters, but your clusters are independent of each other. So you have that independence to hang on to. What if you do crossed effects? If I hold out like the last 10 rows, they're correlated with my hold-in data because they share columns. If there's some effect that's in a column, it correlates my holdout with my hold-in. So it's almost like you're in one of these, my sample size is n equals 1 of whatever I got situation. And so you can have I have a subjective difficulty ladder for how hard it is to generalize. The IID case is kind of the easiest. Hierarchical model, you could think of it, well, it's IID sampling of more complicated things, but you have that IID going for you, or independence anyway. And then time series, the dependence, you think it's going to decay, you have to guess a little bit about exactly how it decays. And at the far, far end here, networks, that really looks like, you know, your LinkedIn network or your Facebook network. It's one big glob, n equals 1. How do you break it into little pieces that have been resampled and replicated? I mean, there are ideas for how to do that, but you wouldn't necessarily know when to trust it for real. And so I'll situate cross defects right in here, right in between. So pretty hard, but not the most hard. A big divide is between balanced and unbalanced data. So if you see all the IJ pairs together, then it's balanced and it's a lot easier to deal with. But our cases are very unbalanced. We'll call the first factor a row. And so rows go from 1 to R. And the second factor will be a column, and the columns go from 1 to C. And then Zij, it's 1 if we got the data for the IJ pair. So the data for the IJ pair is Xij and Yij. We either got them or we didn't. If it's a 0, we didn't get those. And then we're going to need extra indices. So it won't just be I and J indexing our table. We'll also use R and S. Well, Zij is a 1 if we saw observation Ij. If we sum that up over J, then we get the number of data points in row I, or the size of row I. We can also get the number of data points in column J. We just sum over index I. And the total sample size, it's the sum of the row sample sizes and the sum of the column sample sizes. Now, in our assumptions, we're going to assume that there are a lot of rows and columns, way more than 1. But the number of data points is way more than the number of rows and columns. And the number of data points, however, is way less than the number you could have got. Maybe you only saw 1% of all of the combinations, or even less. So this is the range, the ranking of dimensions. 1 is way less than R and C, which are way less than N, and way less than R times C. Here's how our pattern of Zij's could really look. So I'll put a dot if it was a 1, a big dot if it's a 1, and a tiny dot or invisible otherwise. If it's balanced and you see every row with every column, then you have this grid. That's the easy case. That's the case we don't have. You could have rows nested in columns. So the first column had rows 1, 2, and 3, and then rows 4 and 5 were in the second column, and so forth. And you never see 2 data points in the same row. The rows are nested in columns. That's a hierarchical structure. And of course, it could be transposed, columns nested in rows. Down here, if you never saw the same row twice, and you never saw the same column twice, you're basically in an IID setting. You have no chance to learn the random effect variances then. We're in this arbitrary hodgepodge. It is what it is. It's just this arbitrary pattern of what was observed and what wasn't. That's the world we have to handle. In a lot of these applications, missingness is informative. TV ratings are usually biased high. Restaurant ratings could be biased low and high, we think. We're not going to handle missing informativeness. First of all, to do it, you have to make this untestable assumption. Your numbers on a 10-point scale, maybe it really goes to 11, but all the 11s were missing because people were shy to show you the 11s. You could have, it just takes facts from outside the data. It's impossible looking at the data to tell that the things were informatively missing. So we'll forget that. The problem's hard enough anyway without missingness. I have a hunch that some kind of clever propensity methods would help. Now let's contrast ordinary least squares with generalized least squares. In this cross-random effect setting, you could actually run ordinary least squares. It would be consistent. You should actually run generalized least squares using the covariance of the data. And here's what these quantities are. X is a big matrix with all of the predictors Xij in them, 1 per row, so there are n rows, And then there are p columns if there are p of these xij's. And then I don't necessarily care what order you put them in, but when you make up a vector y, it should be a compatible order with how you set up the x's. And then the covariance of y will be an n by n matrix, again, with compatible indices. And I want to note that we're thinking that x and beta are p-dimensional, and we're not going to let p grow with n. So p will just be, 30 in our numerical example. It won't grow with n. Well, you shouldn't really do ordinary least squares. There are two problems with ordinary least squares. The first, ordinary least squares is inefficient. The variance you get is more than the variance you should have got. So you'll have low power. Oh, not just low power, you're going to get type 2 errors. You're going to miss things. Ordinary least squares is also naive. The variance you think you have can be way less than the variance you really have. Oh, so then you're going to get false discoveries. Those are type 1 errors. Usually there's a trade-off. You're going to either get more type 1 errors or more type 2 errors, but OLS can give you both. It can give you more type 1 errors and more type 2 errors. That's not something we often see. So it's not always a trade-off between the kind of errors you're going to get. Sometimes you can get more of both kinds of errors. Let me illustrate for you what this covariance matrix looks like. We have a tiny data set with 3 rows and 4 columns. And of those 12 points, 8 are observed. Okay, so here it is sketched out, rows 1 to 3, columns 1 to 4. We saw this one, but not that one. Now let's label these, arbitrary labeling 1 to n. So we just shoot in numbers, 1, 2, 3, 4, up to 8. And so observation 7, well, that guy's in row 3 and column 2. Now let's look at the correlation pattern in our data. These are the row effects, A sub I. If you got the same row effect as the same person as somebody else, then it's the same row effect and the correlation is 1. Observations 1 and 2 are in the same row, so perfect correlation. 3, 4, and 5 are the next row, 6, 7, and 8 are the next row. Correlations are 0 off of that block diagonal. Now let's look at the column correlations. Observations 1 and 6 are in the same column. 2, 3, and 7 are in a column. 4 is all by itself. 5 and 8 are in a column together. So this is a block diagonal correlation matrix for the column effects in a different order. Let's put everything in row order. Now our covariance matrix is sigma A squared times the block diagonal plus sigma B squared times the scrambled up block diagonal plus sigma E squared times the identity. That's the covariance matrix. Well, when you want X transpose V inverse X and X transpose V inverse Y, you need V inverse somebody. You need V inverse times a column of X or V inverse times a column of Y. That's what you have to get. And you can't Sherman, Morris, and Woodbury your way out of it. So that's just what it is. You can't get it by cleverness, unless there's some structure. If there's a compatible structure here, then maybe you could do it, but we have data that are higgledy-piggledy, and you don't get a structure. Okay, well, if we wanted to invert that matrix V or solve an equation, naive algebra would cost you n cubed work. It's not quite as bad as that. The actual algebra is the cube of R plus C, rows plus columns. Now, R times C is more than n. So one of those has to be more than square root of n. And so if you cube the sum, it's got to be more than n to the 3 halves. And it can be actually a higher power of n. But the best you could get is n to the 3 halves. So the upshot is, if you're in the cross-random effect world, your cost is superlinear. The nested world, it's all linear. Sherman, Morris, and Woodbury help you. Here they don't. And we tested this. I think the best code you can get for linear mixed models and generalized linear mixed models is whatever Doug Bates does. And then we test his code, and the theory comes out. It really does cost you n to the 3 halves work just to compute a Gaussian likelihood one time. So just one value of beta. You can't even get the likelihood in budget. What about Markov chain Monte Carlo? Well, I mentioned this result. And every time, so it didn't work with Gibbs. And every time you tell a Bayesian expert that it didn't work, they tell you that you didn't use the right MCMC algorithm. And of course they're right. So in the nested case, it works like a charm. And then Caitlin actually tried about 9 different Markov chain Monte Carlo algorithms. Not one of them would work on our problem. And recently, Bates and company, they actually took LME, they took Bayes out of LME4, not because Bayes was unreliable, but because computing Bayes is unreliable, at least in their setting. And if you look in the literature, there's oodles of papers on nested MCMC and very few for crossed settings. Now, there really is an MCMC that's better. We didn't know about it, but we found out about it later. Okay, so those are MCMCs. And what is the state of the art? In econometrics, what they do is they run ordinary least squares. So they're inefficient, but they're clever about it and they're not naive. They use a Huber-White, actually not the Huber-White you know, but it's like a clever Huber-White for that setting. And they can get non-naive OLS. Caitlin and I did something different. We just went back to the 1890s and said, let's use the method of moments. And we did it in a way that's inefficient, but not naive. And it does become efficient if one of those random effects would be negligible. You don't even have to know which one, but if one of them is negligible, then you'll get efficiency. Recently, Papaspiliopoulos, Roberts, and Zanella published a Bayesian method that we think works. It's a collapsed Gibbs sampler. I think it's the right way to do Bayes. And James Jondro told me the same idea when I was talking to him about these difficulties. Okay, so I'll call this PRZ from here on. So what's cool about PRZ? Well, they analytically integrate the intercept out. If you find the intercept is correlated with the sum of the AIs and it's correlated with the sum of the B sub J's, and they just take it out analytically. That's the part I like. What I don't like is they had to assume that every row had the exact same number of observations and every column too. So that means every person rated the same number of garments and every garment got rated by the same number of people. So that's not good. Then their mixing time, you have to read the paper quite a few times, but it's little o of 1 times an unknown. And okay, I understand the 1. The unknown is the mixing time of a related Gibbs sampler. And they don't really analyze the mixing time of that related Gibbs sampler, at least not to my satisfaction. No, I have more about that on a later slide. Okay, well, when Caitlin was presenting this one time, Trevor said you should just use backfitting. We thought we were because we alternated between estimating beta and sigma, but he had something else in mind. And there's this result by Robinson. If you're going to do generalized least squares, the solution is obtained by minimizing this regression. We take y minus your original regression, and then you subtract out estimated A's and B effects and put on a ridge penalty. Okay, so the new ingredient here is this matrix ZA, and it's got one observation, one row for every observation, and there's an indicator variable for every row in the original data set. And then this ZB has an indicator for every column in the original data set. So this is just regression on dummy variables. You put the original variables and then your 2 kinds of dummy variables, and then you put ridge penalties on it. And the ridge penalties are ratios of the variance components. And then what do? You estimate A, then you estimate B, then A, then B, you alternate. So it's block coordinate descent or Gauss-Seidel. That's it. Wait, how can that seems really easy. How does that actually make the difference? Okay, let's poke into that. If you have one random effect, then your model would have dummy variables for that effect, and you would be doing this least squares thing per Robinson, and then you'd get the normal equations. If we differentiate this with respect to beta, then we get this normal equation. And if we differentiate with respect to A, we get that normal equation. And if you solve those two together, you get that, well, ZA times A hat. So that's a vector of length n that plops everybody's row effect into their data point, into their data. and you get matrix, matrix, matrix residual. Okay, so y minus x beta hat, that's the residual after you regress on x times this thing here. And Trevor calls that a smoother matrix. So we'll call it S sub A, smoother matrix. Okay, and what is that smoother matrix doing? These are binary vectors. What it's really doing is taking row averages and shrinking them with a ridge shrinker parameter lambda. So it's just the average, it's just a shrunken row average. And then what's beta hat? Ooh, what is that? That's GLS, where the covariance is identity minus smoother. So that's, anyway, that's how it works if you do one random effect, but you don't need to backfit for one random effect. If you have two random effects, you can update the A's with an A smoother, update the B's with a B smoother, and just alternate. And in this paper, they prove it converges. And what do you get when you've done that? Well, you've got a two-factor smoother matrix, or an implementation of it. And then we can do a two-factor smoother on Y and a two-factor smoother on all the columns of X, throw it all together, and then we have our generalized least squares. And the details are on arXiv now. And it costs order n per iteration. Each time we iterate, it costs us order n. That's, oh, wait a minute, how many iterations? We better be careful. It would be bad luck if it cost us order n per iteration and we needed square root of n iterations. We don't want that. So most of our work was showing that the number of iterations can be bounded as n goes to infinity. We can do a little better by centering it. We know that at the solution, the A hats sum to 0, and so do the B hats. And so instead of making the iteration discover that fact, we can just bake it in. It's very analogous to the collapsed sampling. You could bake it in by centering. Every time you get a new A, you could just subtract the average. And you could center the B's if you want. And then what's this average? Well, it's just the average of the AI. Okay, so if we did that centering, we're giving it this strong hint that the A hats are going to add up to 0, so we might as well make it so. We can be a bit more principled about our centering. If we minimize over A, here's an arbitrary response regressed on the A's with a ridge penalty, and the A's sum to 0. Okay, well, you can work out the minimum of that quadratic. And if we take the sum of that response in row I, and we put weights that are inverse to n plus lambda, okay, so inverse to sample size, but normalized. Anyway, in that world, the update becomes take the sum in that row, and if we just had the sum in that row divided by n, that would be the row average. But oh, this lambda means we have a shrunken row average. Oh, this means we have a centered and shrunken row average. So take this, center it, shrink it, and that's the update. Okay, now I'll tell you about Stitch Fix. One of our former students, Bradley Klingenberg, is there. He left working in the finance industry, doing high-tech finance, to go and originally sell women's clothes. Now they sell men's clothes. And they'll have a stylist, a human, will look at the AI data and pick out 5 items to send to the client. And then the clients will buy some and return the others. So our factors are the customer and the thing the customer got. And then there could be features like the size, what it's made of, how much it costs. They'll have lots of data like that. And then here's our same old model. Today we're going to look at the response, whether they liked it on a 10-point scale. Obviously it's important whether somebody bought something too, but it's even more better if they really, really liked it, if they bought it and they're very happy about it. So a 10-point scale is actually useful beyond just did they buy it or not buy it. They sent us 5 million ratings, about 760,000 clients, and about 6,000 items. And this is only a tiny set of their data, not representative. They wanted us to say that. Also, the data is more than 5 years old, so it's not going to, saying this isn't going to help any of their competitors. And then what are the predictors? One of them was a match variable. Some other algorithm gives you a match of how good item J is for person I from some baseline model. They also told us whether an item is edgy. Now, I'm not a fashionista. I'm not totally sure what makes something edgy. And then also the client could be edgy. And then there's another thing, boho. The item might be boho, or the client might be boho. And then there are material types. Is it polyester, leather, fur, etc.? So those are the variables that we're using. We had 30 variables. Okay, so what will we do with this? What we're going to do is look at the first regression model we thought of. Of course, if I worked at the company, I'd look at dozens of regression models and try all kinds of things. But here I just want to compare OLS and GLS. And so I'll just pick one model. And we need to get those variance components. But Caitlin showed that you can get consistent asymptotically normal estimates of the variance components in order n work. Okay, so check out her thesis where she shows that they're asymptotically normal. So that'll get us the lambdas that we need. But now we need to do GLS. And here's our regression model. So 10-point scale of how much they like the item, intercept. There's that match. Did their old algorithm really predict that well? Here's something if the client is edgy. Here's something if the item is edgy. Here's something if they're both edgy, because maybe it makes sense to send the edgy item to the edgy client. And then same for boho. And then this beta 8 is really a bunch of betas, indicator variables for all of the materials. And the most common material was polyester, so we took that as a baseline. So you can think of the intercept as being or you can think of the coefficient as the difference compared to polyester. And when we looked at this, we found that, edgy items might not be that popular, but the edgy clients kind of like a lot of things, and it really is a win to send an edgy item to an edgy client. And we couldn't make it work for boho. And it just didn't seem that there was any way to, the people don't like the boho items as well as the other, compared to the other items. And even the boho people don't seem to in that data. Okay, I told you that ordinary squares is inefficient. What does that mean? Well, here's the variance that you would get for ordinary squares for variable j. And here's the variance you could have got if you did generalize these squares. And so you're getting more variance and almost 50 times as much variance in some cases. And so here's a histogram of those variance ratios. Let's zoom in on 5. If your variance ratio is 5, so you get 5 times the variance you should have, it's like you just ignored 80% of the information in the data. And of course, 10 would be like ignoring 90% of the information. And 50, well, who knows? Don't do that. Okay, so OLS really comes out to be meaningfully inefficient on this data. And then I told you that OLS is naive. Here's the variance that OLS thinks it has. And here's what we think the variance really is. So the real variance is anywhere from about double to about 300 or more times what you would think from OLS. Because OLS ignores correlations. So let's look at 100. If you're naive by 100, that means your confidence interval is 10 times too narrow. So if you want a 95%, maybe you're going to get 15.5% coverage. Ouch. That's not very good uncertainty quantification. And then for fun, on this axis, we have how naive OLS is. On this axis, we have how inefficient OLS is. And there tends to be a positive association. The things that make you naive make you inefficient. Okay, that was a little data set, peek at the data set. Now let's think about convergence. We want to get the thing done in a finite number of iterations. And we can look at what happens when you're backfitting and you update the vector b. Well, your new vector is linear in your old vector with an intercept and a matrix. We actually don't care that much about the intercept as much as the matrix. And if that converges, then b stops changing, so a stops changing. So it's enough to show that b will get there in a finite number of iterations. And we can solve this if we can do an infinite sum. So we really want the tail of the sum to become negligible quickly. And the way we're going to look at that is through the p-norm of the matrix M. So let's take the most you can get as the p-norm of MB and divide by the p-norm of B for non-zero B. Okay, so this is the compatible norm. And if that is bounded away from 1, so it's below 1 minus delta where delta is positive, then we need only a finite number of iterations. This will keep the spectral radius below 1 minus delta. So that's what we want to do. What does that matrix M look like? Actually, it's really ugly. I'll show you a slightly simpler version of it. So the new A, it's this residual. You shrink B, subtract B, and then take a shrunken average. This is shrunken, this is average. Then you take those new A's and you plug them in over here and do the same thing for B. And when you do the round trip, the matrix M has this form. Ouch. Well, we've got binary variables. Here's a binary variable that got centered. Then the whole thing got averaged and shrunk and then scaled down. Anyway, that's M0. And then if you do centering, we call it M1. It looks worse. Principled centering is M2, looks more worse. Okay, what do? We find conditions on this observation pattern that will keep the L1 norm of our matrix away from 1. And it actually works for this other naive centering too. Okay, so with probability tending to 1, it'll be okay, and we'll have a finite number of iterations. And so what do we need? Well, we need to know about this capital P. What's inside that? And we're going to have a model where R and C both go to infinity, but N is way below R times C. And then we have to decide how these random Zij's are going to control M. And why did we do M? Because we could. It's way more tractable. We'd be better off doing the L2 norm or the spectral norm. We couldn't figure out how to do it. And here's our model. The size of the problem is S, which goes to infinity. And then the number of rows we have is S to the power rho. And the columns we have is S to the power kappa. And our sample size is way below S to the rho plus kappa. And here's our sampling model. It's independent Bernoulli's to see that data point. So Pij is the chance that we saw Ij. And what about these Pij's? Well, they're stuck between S over RC and upsilon times S over RC. And so this keeps the expectation kind of around N, and then we're going to have this upsilon gives us some wiggle room. So in other words, the good news is that our sample sizes are random and unequal. The number of observations in row I can vary with the row I, and same for the columns. We can even make their expected values unequal. So that gives us a lot more realism than the PRZ paper. The disappointing side is that these are still really close to equal. They're only a little bit unequal. And also we can't include the tiny counts that you would get in real data. And so what about this upsilon? Well, the expected sample size is between S and upsilon times S. Now we have a random sample size. Okay, so here's our main result. We need some conditions. So these rho and kappas are between 0 and 1. It needs to be more than 0 so that R goes to infinity. It needs to be less than 1 so that R is below N. And rho plus kappa have to be bigger than 1 so that our total sample size is way less than RC. So that's just turning our assumptions into conditions on rho and kappa, we get this. But we need some extra conditions. We need, we need this condition that 2 rho plus kappa is below 2. And that will control the sample sizes in each row. So we have to keep those close to equal, and this will do it. And then we also need to control the column size, but even more, we have to control how much overlap there is between 2 columns. So if you pick 2 columns, they have to overlap at least a little bit, and this is the condition we needed. Under these conditions, then our 1 norm with probability tending to 1 is below this thing. So here's our epsilon squared minus epsilon to the minus 2 plus epsilon. Okay, so that's what we get. That's how much wiggle room we can get for unequal probabilities. And the most we can get for that epsilon is about 1.27. I would have wanted more, but you get what you get. Here's our asymptotic domain. So the number of rows is this power of S on this axis. And the number of columns is that power. And if you ride down the diagonal, you're kind of getting in expectation a balanced thing with one in every data point. If you never saw the same row twice or the same column twice, you'd be up here with IID data. And our theorem gives us this nice blue triangle of success. And if you transpose it, you would get this additional triangle. So as long as we're in here, this little triangle or this big triangle, the theorem applies. The Stitch Fix data looks like it's around here. Okay, so it's not covered by our theorem. When we run examples out here, it often works. And I think it's because we're only able to prove things for the one norm. Okay, here's the proof. Let me grind it out. The one norm is the max over S of the sum over J of this absolute value. And if J is unequal to S, wow, here's our expression. ZRS is, did we see RS together? This is the average in column S. We take shrunken averages of that, shrink it down again, and then what is that ZS bar? That's actually a shrunken average itself. Okay, upshot of this, it's actually just kind of a mess. So it's really pretty awful. How do we prove it? Well, using Hoofting inequalities, we can keep our row sample sizes strictly in bounds. They're all more than this, and they're all less than that. And same for the column sizes. This quantity here is how many rows did we see column J and column S together? We keep that number in a box for all pairs JS. Okay, so everything's in a box. Now we have to propagate those boxes to M1. And we use interval arithmetic. If you have something in this interval and you add it to somebody in that interval, you end up in this interval. And if you divide, you can do, well, the most it could be is take the biggest guy, divide by the smallest denominator, or take the smallest numerator over the biggest denominator. So we use this interval arithmetic trick just to propagate our probability bounds through a lot of steps and all the way to M1. Here on Stitch Fix, that data, let's see, what did it have? It could have the one norm, two norm, or spectral radius, and we could do sophisticated shrink centering, naive centering, or no centering. Okay, so those are the things we did. And over here, the one norm that we proved things about just was never good, but the spectral norm was always good. And then the two norm was sometimes good if you did the centering. Okay, so the thing is really going to converge, and it took 6 iterations to converge, but our theory doesn't cover it. Here are some simulated norms. We can Monte Carlo from our model. Suppose that rho and kappa are both 0.7. It shouldn't work there. And the one norm starts off like at 1.4, and it just grows as the sample size grows. Okay, so the one norm isn't getting control. But the two norm actually does. The two norm starts off below 1, and it drops on a log-log plot. I think it's heading to 0. We can't prove this yet, but we're optimistic seeing that. Here are some timing data. So here, if you take rho and kappa are 0.5, and then you run LME4, so that's Doug Bates' code, the best code, I think, you would find that the cost grows along this line, and this is a slope 1.5 on a log-log. So we're getting n to the 3 halves. Our backfitting starts here and then grows like order n. And plain ordinary squares also grows like order n. If instead you go to 0.7, things are different. Now LME4 actually grows like n to the 2.1, which of course is triple 0.7. And these backfitting is still growing linearly with n. Let me say a little bit about the results from PRZ. They show that the mixing time, it's this quantity, which for us is 1 because n is way bigger than r, times this other thing, which is also 1, times an auxiliary mixing time. And the auxiliary mixing time is if you have a customer pick a random item that they bought or that they looked at. If you have an item, pick a random customer, then go back and pick a random item, random, customer, equal probability. You're doing a uniform random walk on a bipartite graph. That will have a mixing time. I don't know what it is, but that is basically the mixing time they're going to get. And I'm optimistic that it's good. I don't think they showed it was that good. Okay, so what's left to do? Well, logistic regression, and Swarnadip is well underway, extending this to logistic regression, higher weight tables, SVD interactions. Wow, that would be really interesting if we could get those heteroscedastic effects. So there's more to do. And at this point, what I want to do is thank a lot of people. So I want to thank my co-authors, Swarnadip and Trevor. I'll thank a lot of thanks to Brad Klingenberg for getting us the data and talking it over. National Science Foundation helped us. They supported this work. I had discussions with Giacomo Zanella. I want to thank Walter and Irene and Jean for making all of this possible. And thank you for tuning in. I have time for questions.
Thanks, Art. So I know that with Zoom, some people, there's a lot of people in the chat. So I guess feel free to.
I didn't see the chat. I went full screen, so.
Yeah, no, it's just a lot of people in the. There we are. There's everybody.
Okay.
So anyone who would like to ask a question can turn their mic on and ask it. If we get too many people or my dog starts barking, I'll turn it off. So I'll mute myself.
Yeah, you should let him out.
Okay, I'll ask a question. So you were talking about modeling Zij as random, but these garments are selected by an AI that presumably incorporates already information about the customer. How does that affect your results, or how should we think about that?
Well, actually, that's a good question. We use doublethink. So let me tell you how that goes. What we think is when you're analyzing the data, we're going to take Zij as fixed. They're not random. We'll just assume it is what it is. That's the data we got. Then, so for the person studying the data, the Z's are fixed. And then for us studying the person, somebody in the future is going to get a matrix of Z's. What do we think that matrix of Z's is going to look like? Well, here's an ensemble of matrix of Z's that they might get. And we'll use randomness to model what they might see. So that's our doublethink approach. It's really like you have it's like you have there's two separate time points. There's a time point when you're developing a method for some unknown future data, and there's a time point when somebody's actually trying to use it.
Okay, I see. So then if the Zijs aren't really random, we're really just thinking about the space of possible matrices that someone else might see as being smaller than what you're modeling. Is that?
You know, this comes up in regression. Like, are your X variables random? Well, yeah, but then we condition on them to make them fixed. Actually, what people do is they can analyze the regression with random X or fixed X, and they pick whichever one makes it come out easier. And then, you can talk about something being ancillary.
Sure. Okay.
Yeah. But we wanted to focus on sort of focused on the computational thing. Can you actually do this now?
Mm-hmm. Yeah. Thanks.
Oh, you're welcome.
Art, Jack Colfleisch here. Art, I was interested in your model, the simple model that you had with AI and BJ both being random effects and adjusting for the IJs. We do things not as complicated as you, but one concern, I guess, that arises is that the X's might be correlated with the random effects, and because that model basically assumes they're independent, doesn't it? That the like AI given Xi normal 0, whatever. But is that an issue at all for you? Or?
Well, we're going to assume that, no, first of all, there's a lot that's wrong with that model for these real applications. And then we use the model because it's the easiest one that we can't do. And so in real data, there's just big interactions. Like that epsilon ij, really there should be interactions. In real data, the distribution of AI isn't really the same for every row I. And the AI, if somebody has made a lot of purchases, then their mean invariance of A might be different than somebody that made a few purchases. So it's really heteroscedastic. And then the X's, I think if we treated the X's as fixed, then we'd have to think of, well, what did the A's look like conditional on the X's? So there's a lot going on trying to.
So you don't treat the X's as fixed?
We do, yeah.
Yeah.
We treat the X as fixed and the Z as fixed and then try to do GLS.
Yeah.
And a lot that's wrong.
The point is, maybe you've covered, I don't understand, but my point is that in that model, it's a model for Y given X, right?
Yes.
And so the distribution of A and B is also given X.
Yeah. That's the one. That's the way to say it. That is A and B given X.
And that model assumes they're independent.
Yeah. And then, I think what people really do, is they would take these factors and turn them into thousands or millions of categorical variables, and then run something like a neural net or lasso or support vector machine or something on those categorical variables with some kind of regularization.
Mm-hmm.
And none of those tools ask you whether you think those things are fixed or random effects.
Yeah.
Like I don't think you, when you're setting up a neural network, I don't think there's a place where you say, yeah, this is a random effect. Or even I think in Lasso, I don't think there's a place where it's asking you, is that one fixed or random? So I wonder what happens.
Yeah.
Like, are they naive? Are they inefficient? I'm guessing they're kind of efficient, but maybe naive. Yeah. Yeah.
So Dr. Owen, Peter Song, and I have a question. So have you ever considered use this kind of model to have some clustering? Because A and B representing some latent features that you cannot capture by the X variables, your columns like customers, items.
Yeah.
Do you think it's possible to use model to capture some clusterings, like some of items are clustered, and rather than just fit them by this, simple random effects model, maybe there's underlying groups like you want to capture through your model?
I believe that would be a much better model, and I would be much happier if I could fit that. And I think maybe even a bicluster where you say these products are good for those customers and these other products are good for these different other customers. That's what I would really want. And until this work, we couldn't even get the simple model we have. Like n to the 3 halves is such a blocker. But no, those are exactly the kind of things people want to get. And I think they have methods of getting them, but I don't know if they get the uncertainty quantification. Like there's an old paper by Peter McCullough, and he proves there's no bootstrap for this problem. Even if the model is just an intercept plus random effects, and even if all the data are observed, there's no bootstrap that exists. And then, so you can sort of bootstrap the rows independently of the columns, and then you get an overestimate of variance. And then there's other work I've worked on with Patrick Perry where we try to cross-validate. So you hold out some of the rows and some of the columns and use the held-in corner to predict the held-out corner. So I think maybe that stuff could be used if you have a way to find biclusters.
That's right. I also see some of the connections of your work to this smoothing splines. You know that they can turn this smoothing spline into this very, very sort of large vector of random effects, and sort of this connection of the non-parametric regression and the way that you present it. I think that could be a direct application to fit some of this sort of the smoothing spline with a lot of data points. Yeah.
Okay.
So that's the Simon Wood and Shi Honglin and some of the people in this department developed this kind of way of using error to like rich penalty to estimate the non-parametric functions in the context of smoothing spline. So that I think there's a direct connection, and your method, your fast algorithm can apply to that situation as well.
Can you send me some links?
Yeah, I will. After the talk, I can certainly send you the paper. Yeah.
Yeah. So, so the backfitting thing came from Trevor Hastie and his co-authors thinking about smoothing.
Yeah.
And so then later, if I get it right, they would just build in, oh, if you had a categorical variable, then this is what smoothing would be.
Yeah.
Yeah.
Yeah, I can send you the paper that how things are connected. Yeah.
It sounds like it might work well on climate data and
that's true.
Geographic, geophysical data.
So I'm trying to very good talk first, Art. Yeah, I'm trying to understand your conditions. I'm go over pretty quickly. So basically, you're saying that the row sums and the column sum, they're sort of close, right, for every single row and column?
That's what we had to assume.
So in that sense, if, for example, you talk about 3 cases in the beginning, one of the cases is totally nested, that one won't work?
That won't work, yeah. Well, actually, if it's nested, then your life is so much easier that you don't need this.
Okay. Yeah. And the other one is the full case fully connected, would that work?
When it's, well, when it's fully
complete
connected,
data,
and you've observed everything, then it's kind of easy to find something that works. Yeah, when it's completely fully observed.
Okay, so I just wonder if I give you a random sort of a matrix and which doesn't really follow your condition, could you do a subsample to make it follow your condition and just run on a subsample?
Oh, I think that would be pretty tricky because I'll give you a matrix of dots, and then you pick a subset so that all the rows are almost equal and all the columns are almost equal. I mean, it's harder than Sudoku, I think, to do that kind of subsetting. And then I also think that we don't really need it. We needed that for our proof, but the real data was nothing like that, and the thing still worked.
But have you find real data where it doesn't seem to converge that quickly?
We can break it. One way to do it is populate the first 10 rows and columns together, and then the second 10 rows with the second 10 columns. So make 2 perfect blocks that don't intersect, and then it breaks. And the irony is you just have 2 really simple, easy problems, and you put it together and you get an intractable problem. So that's some weirdness, and it's because the row indicator variables overlap in space with the column indicator variables. You could do canonical correlation and find there's some linear combination of row indicators that exactly equals a linear combination of column indicators. And if that's going on, how can you tell what's row and what's column? Yeah, so our assumptions are way stronger than what we think is needed. But at least we don't have to assume that it's exactly equal row counts and exactly equal column counts.
Thank you.
Yeah, all right, you're welcome.
If there's no other questions, I mean, just to remind everyone, there is a discussion tomorrow at noon, so you can read the paper and come up with a lot of questions before then. But let's just thank the speaker, I guess, however you can on Zoom. So thanks again to Art for giving a great presentation, and we'll see you tomorrow.
Well, thank you, guys. Bye-bye.
Bye-bye.
Good to see y'all. I miss Zingerman's too. Mm-hmm.